Hey guys, today I'll be going over question 2 of the AP Physics 1 2024 exam. So over here we have a student hangs a spring of unknown mass of spring constant K vertically by attaching one end to a stand as shown in figure 1. The other end of the spring has a small loop in which small cylinders can be hung. So as you can see, the hook goes over the loop and the cylinders can be hung over it like so. In addition, the student only has a variety of cylinders of unknown masses, a stopwatch, and a digital scale. So, question A asks to design an experimental procedure the student could use to determine the spring constant K of the spring. And we need to list the quantities that would be measured using only the provided equipment and define a symbol to represent each quantity. In the space below, describe the overall procedure. Provide enough details so that another student could replicate the experiment, including any steps necessary to reduce experimental uncertainty. As needed, use the symbols defined in your table, and you can include a simple diagram. So, first of all, we need to fill out this table. Well, for the first two rows, we already have the symbol. We have stopwatch, which measures time, and digital scale which measures mass. So for the symbol, we could just do T and M for mass. Now the quantity to be measured, well, for stopwatch, you would need to measure the time, but what part of the time do you need to measure? Do you need to measure the time that the cylinder takes to just go down or to complete a full period? Well, if we go all the way up to our equation sheet, we realize that the period can be defined as an equation which contains a spring constant, and that is probably the equation we're going to use. And that equation is T equals 2 pi root m over k. So the time in this case would be measuring the period, and the mass would be measuring the mass of the cylinder. So time per period and mass of cylinders. Now, as you can see here, if we already have the time per period or just a period and we have the mass, we could just directly solve for k. So in this case, we won't need another row. So we could just leave that blank. The procedure and diagram if needed. Well, what I would do is I would get a cylinder and I would put it on the mass. I would start the stopwatch and release it and time the amount of time it takes to complete one or two oscillations. But make sure if you're timing two oscillations divided by two. I feel like that would reduce uncertainty, but you'll need to be more precise in answer. So let me create a text box here. Okay. One. So what you need to do first of all is you need to measure the mass of the cylinders. So weigh the cylinder, weigh the mass of the cylinder on the digital scale and record it. So number two, after you have the mass, you could just directly hook it onto the spring. So two would be hook hook the cylinder onto the spring stand. Number three would be release the cylinder from rest because you're originally holding the cylinder from rest and start the stopwatch because you want to measure the amount of time it takes for one whole oscillation. So once you release it from rest, that time starts. After the cylinder. So when we stop the stopwatch, it would be after one whole period. And when do we know the period ends? It's when the cylinder comes back to its original position at its maximum height. So after the cylinder reaches its maximum height again, stop the stopwatch. And finally, record the time it takes. Just record the time on the table. So now you have the weight of the cylinder and record the time it takes. But um, the question also asks to include any steps necessary to reduce experimental uncertainty. In AP Physics, any type of AP Physics, they will ask you this. And a good way to do it would be to repeat steps 2 to 6, to 2 to 5. I would just stick with 5 times. Even if in real life you don't need to do 5 times, it would be better because you can't go wrong with going over. But if you do it too little times, you might get deducted steps. And after you did this 2 to 5 times, you can repeat steps 1 and 6 all over again with a different mass. So repeat steps 1 to 6 with a different different masses. And yeah, that would be your procedure. So indicate the quantities that could be plotted to produce a linear graph whose slope can be used to determine the spring constant K of the spring. Okay, in order to do this, we know that slope is delta y over delta x. So if K equals delta y over delta x, then we need to find delta y and delta x using this equation. So t equals 2 pi root m over k, and we would manipulate it to solve for k. Well, first off, what I want to do is I want to divide both sides by 2 pi. So t over 2 pi equals root m over k, and I would square both sides. T squared over 4 pi squared equals m over k. Now we cross multiply, and we get m times 4 pi squared over t squared equals k. And now we have our delta y and delta x. Delta y would just be m. This is a constant, so remember, a constant doesn't matter. Even if there's a constant here, the slope would be the same. So you could just do vertical axis would be m, and horizontal axis would be t squared, the period squared. Briefly describe how the slope can be analyzed. Okay, well, we already solved for the slope, so actually it would be better if you put m times 4 pi squared, because this way you can directly get the slope here. So um, when you're describing it, you could say, so what? When you're describing it, you could just say the slope of the graph is equal to the spring constant. And that would be enough. In a different experiment, the student attaches one end of a spring to a force sensor that is attached to the wall. The other end of the spring is attached to a cart with a mass of 0.25 kg, and the student places a motion detector to the right of the cart, shown in figure 2, and pulls the cart to the right a small distance so that the spring is stretched. Okay, and then the student releases the cart from rest, and the cart spring system oscillates. So basically, what is happening is this is a spring, and the cart initially starts out a distance away from equilibrium, and when it releases, it's going to oscillate back and forth. And the following graphs show the velocity of the cart and the force exerted on the cart by the spring as functions of time. So this would be velocity over time, and this would be force over time. And using the data in the velocity time graph, calculate the kinetic change in kinetic energy of the cart from t equals 0.5 seconds to t equals 2.0 seconds. Show your steps and substitutions. Okay, so we know the mass of the cart. So this should be easy because the change in kinetic energy, delta KE, would be the final kinetic energy at 2 seconds, final, minus the initial kinetic energy at 0.5 seconds. So 1 over 2 mv final squared. This is the formula for kinetic energy. At minus 1 over 2 m initial squared equals, before we substitute everything, it would be better to factor out this. So 1 over 2 m vf squared minus vi squared. And I do this because I want to reduce the possibility of error when I'm typing this into my calculator, because I don't have to type m 2 times. So always reduce your equations before substituting real numbers in it. So now we can plug in real numbers. 1 over 2. The mass is equal to 0.25 kilograms. The final velocity would be the velocity at 2 seconds. So that would be about 0. So 0 squared minus the initial velocity would be at 0.5 seconds, which is 0.3 meters per second. So 0.3 squared. And when you type that into your calculator, times 0.25 times 2.3 squared negative 0.01125. 0.01125, and the unit for kinetic energy would be joules. And this would be your final answer. Using data in the force time graph, estimate the change in momentum of the cart from t equals 0.5 seconds to t equals 2 seconds. So 2.5 seconds. So pulling out my equation sheet, I can recall that there is an equation that relates the change in momentum to the force. And that formula is F net equals delta P over delta T, where P is momentum and T is time. So from 0.5 seconds to 2.5 seconds, the change in force, the net force, would be equal to 0, because at 0.5 seconds, the force is at 0, but at 2.5 seconds, the force is also at 0. So the net force is 0. And so we can plug this in. 0 equals delta P, the change in momentum, that's what we're trying to solve. And T would be, delta T would just be 2.5 minus 0.5, which is 2. So when we solve for delta P equals 0. And in a real exam, you would explain this. So I would say something like, the change in momentum of the cart from 0.5 seconds to 2.5 seconds, it would be 0 Newton seconds. Since change in momentum is equal to the net force times the change in time, as you can see here, if you just rearrange it, delta P equals F net times delta T. If the net force is equal to 0, then the change in momentum is equal to 0. Did I say that right? Is net force 0? Yeah, net force is 0, but not because what I said. Net force is 0 because the net force is just the area under the curve. Because it's a function of time, you can't just do delta F. So, however, the area under the curve, the total area under the curve is equal to 0 because this is the negative version of this. So the total force would be 0. And do the data from the velocity time graph confirm your estimation from part CI? So we know that, well, first of all, if it asks these questions, the answer should most of the time be yes, unless you know you got this wrong, then you would say no and try to get partial marks. But in this case, I don't even need to look at the graph and say why. Well, we know that the momentum equals to mass times velocity, and since mass is constant, velocity on the velocity time graph should be constant. Let's see, from 0.5 seconds to 2.5 seconds. Yep, they are both at 0.3 meters per second. So the momentum would be constant. So what I would write is yes, the data confirms my estimation. This is because the velocity at t equals 0.5 and 2.5 seconds are the same, and the mass of the cart is constant. And what would the mass be? The mass is 0.25 kg. Since momentum is given as P equals mv, if m stays constant and v stays constant, the momentum stays constant as well. Since the momentum stays constant, always tie it back to the question. Since the momentum stays constant, this confirms my estimation. Another way you could do this is by doing delta P equals m delta V. It's basically the same thing, but probably a more accurate and scientifically accurate approach. And you could say that delta V equals to 0, so delta P must be equal to 0. And that's all for question 2. Thank you for watching.